Hi everyone, my name is Prabhat. I am studying in VIT University, BTech first year CSC, and my registration number is 17BC0337. Okay guys, let us have some brief introduction for quantum mechanics. Quantum mechanics. Before going to quantum mechanics, first we relate the classical physics to visible world. Coming to matter, on behalf of classical physics, matter can be defined into two types by its characteristics. One is particle nature and the other is wave nature. Coming to particle nature, what is a particle? A point-like mass that moves along a trajectory in 3D space is known as a particle. Whereas coming to waves, it is not localized in space. Whereas particle nature, again coming to particle nature, position and instantaneous velocities can be determined with an arbitrary high precision at any time. Whereas in wave nature, it has a velocity of propagation known as phase velocity. Coming to particle nature, the time evolution is predictable from equation of motion, whereas in wave nature, waves are characterized by wavelength or frequency. Next, the laws of particle motion, that is known Newtonian mechanics, accounts for the material world around us, and the laws of electromagnetic field accounts for the light waves which illuminate this world. These are the Maxwell's equations. This is known as divergence of electric field. Divergence of electric field is rho by epsilon naught, whereas this is known as curl of electric field. Curl of electric field is equal to minus dou b bar by dou t, which is a partial differentiation of b bar with respect to t. Whereas coming to this is known as divergence of magnetic field, which is equal to 0. Whereas coming to curl of magnetic field, it is equal to j bar plus dou e bar by dou t bar, this is a partial differentiation of it. Classical physics failed to explain two domains. One is relativistic domain and the other is microscopic domain. Relativistic domain. In relativistic domain, Einstein theory of relativity, which was proposed by Einstein in 1905, states that Newtonian mechanics ceases at very high speeds, that is approximately equal to velocity of light in vacuum. Whereas coming to microscopic domain, stability of atoms and properties of subatomic particles such as black body radiation, photoelectric effect, Compton effect, atomic stability and atomic spectroscopy, which cannot be explained by classical ideas. There are certain limitations in classical theory. These limitations are in stability of atom and hydrogen atomic spectra. Stability of atoms. According to Rutherford, negatively charged electron is moving around the positively charged nucleus in circular orbits, which means there are some attractive forces between electron and nucleus. Since the electron is moving around the nucleus, centripetal acceleration is developed. Accelerated charged particles emit electromagnetic radiation, which leads to a continuous decrease of the electron energy, resulting in a collapse of the atomic structure. Coming to hydrogen atomic spectra, when an electron jumps from higher energy states to lower energy states, there is a series of spectrum lines which can be explained here. See, when from higher energy states to n equal to 1, when an electron jumps, it is known as Lyman series. When an electron jumps from higher energy states to n equal to 2, it is known as Balmer series. When an electron jumps from when an electron jumps from higher energy levels to n equal to 3, it is known as Fashion series. Similarly, when an electron jumps from higher energy levels to n equal to 4, it is known as Bracket series. Finally, when an electron jumps from higher energy levels to n equal to 5, it is known as Fund series. Discrete atomic line spectra observed in a hydrogen atom could not be explained by classical physics. Here, mu bar equal to RH into 1 minus n1 square by n2 square is the formula for wave number. Here RH is known as Rydberg's constant, and N1 and N2 are the higher energy level and the lower energy level of a specific series. Idea of quantization. The idea of quantization was first thought by Newton, and he proposed a theory named Newton's corpuscular theory of light, where light consists of minute fast moving elastic particles known as corpuscles. This theory could not explain the wave properties of light, such as interference, diffraction, and polarization. The second thought was idea of quantization came to Huygens, where he proposed a theory, Huygens wave theory. Here, this theory states that a light travels through propagation of wavefronts in a hypothetical medium. Generally, this medium is ether. This theory could explain the wave properties of light but failed to explain photoelectric effect, Compton effect, and black body radiation. These problems led to the birth of quantum theory of light. Our next topic is Planck's radiation theory. In 1918, Planck got a Nobel Prize for his lucky guesswork, which is the beginning of modern physics. Planck succeeded in giving an accurate description of black body radiation, and UV catastrophic was avoided here. According to Planck theory, energy exchange between radiation and matter occurs in a discrete manner, and this theory states that energy of radiation emitted by oscillating charges electrons from the electrons from the walls of black body cavity must come only in integer multiples of h mu, where here which means here we got a formula E equal to n h mu, where E is the energy and n is numbers from 1 2 3 so on, and h is the Planck's constant and mu is the wavelength. Here h mu is the energy of one quantum packet of radiation. Next, Planck's radiation theory states that emission or absorption of radiation occurs only when there is a change in quantum state. Since standing waves involve the oscillation of electrons, they can be considered as oscillators, and each oscillator emits or absorbs radiation in packets or quanta. By this we get a formula of average energy per Planck oscillator, which is equal to h nu by exponential h nu by kt minus 1. As we know the average energy per Planck's oscillator, here we get a term known as spectral energy density, where U into V of dV equal to 8 pi V square by C cube into h nu by exponential of h nu by kt minus 1 into dV, where here this term is known as spectral energy density, and this term is we already know that average energy per Planck's oscillator. This formula is known as Planck's radiation formula, and this spectral energy density in the high frequency limit it becomes 0, and at low frequency limit it resembles Rayleigh-Jean's law. Next we are coming to photoelectric effect. In 1905, Einstein showed the particle behavior of electromagnetic radiation through photoelectric effect. This photoelectric effect states that energy of electron liberated from a metal surface by electromagnetic radiation depends on the frequency of incident radiation, where here finally got h mu equal to ke plus 5, where here as we know before h mu is the energy of one quantum packet of radiation, and ke is the kinetic energy of emitted electron, and phi is the work function of metal, which is equal to h mu naught, where mu naught is again threshold frequency. And an increase in intensity alone can in no way dislodge electrons from metal, but By increasing the frequency of incident radiation beyond a certain threshold, even at very weak intensity, the emission of electrons starts immediately. By all this, the concept of gradual accumulation or a continuous absorption of energy by the electron as predicted by classical physics is indeed erroneous. Our next topic is about Compton scattering, which was proposed in 1923. Most most conclusive experiment for this is the most conclusive experiment for the particle behavior of radiation. Here we see a target which where an X-ray source from an X-ray source ray is coming and colliding a target and here we can see this diagram by where this ray goes like this and comes like this, where this passes through a collimator and reflected by a crystal, and finally it is detected. By this we get when we plot graph between intensity and wavelength, we can find the graph like this for a primary beam where theta equal to 0 we will get like this. After that it becomes when theta equal to 45 it will be like this, and here lambda naught and lambda t are peaks where we can find here. I will explain here. And after this like this when theta is equal to 90 and when theta equal to 135 it will be like this, where here we have to consider a collision between a photon and an electron. Finally the result of this is scattered radiation peak, which I am talking about. This scattered radiation peak shifts to longer wavelength than source. Here wavelength shift depends on scattering angle, not on incident wavelength. Classically, the incident and scattered wavelength should be the same. That is, in another view, since the energy of the X-ray radiation is too high to be absorbed by a free electron, the incident X-ray would then provide an oscillator electric field which sets the electron into oscillatory motion. Hence, electrons should radiate light. With the same wavelength, electrons should radiate light with the same wavelength but with an intensity I, which depends on the incident radiation intensity I naught. But experimentally, it was observed that it increases by a factor delta lambda, which depends only on the scattering angle. Compton succeeded in explaining his experimental results only after treating the incident radiation as a stream of particles. Photons collide elastically with individual electrons, and hence both momentum and energy is conserved. By quantum effect, we can conclude that loss in photon energy equal to gain in electron energy. Using the conservation of energy and momentum, the quantum shift can be derived as lambda dash minus lambda equal to h by m naught c into 1 minus cos phi, where here phi is the angle between incident and scattered photon. When when phi is equal to 180 degrees, maximum kinetic energy is impacted to the scattered electron. Since quantum scattering does not depend on the incident wavelength lambda, delta lambda by lambda is much pronounced in X-rays than in visible light. Finally, let us see what we have covered in quantum mechanics. First, we have started with classical physics, Maxwell's equations, failure of classical physics, limitations of classical theory, idea of quantization, Planck's radiation theory, photoelectric effect, and Compton scattering. The remaining part can be explained afterwards. Thank you very much.